Okay, conservation of mechanical energy. So the mechanical energy in a system is the sum of the potential energy and the kinetic energy. So we've looked at gravitational potential energy. We will also go on to look at elastic potential energy. So if you've got a spring that's being held down and stretched, then there's some energy stored in the system from that. So we'll go on to look at that as well. So there's different types of potential energy, but at the moment we're just worrying about gravitational potential energy and kinetic energy. Conservative forces conserve mechanical energy. So, for instance, gravity is a conservative force, and tension in a spring even, is a conservative force. So if you lose potential energy and there's no other forces acting, it will get converted to another form of mechanical energy. And that's what we're going to start by looking at today. Dissipative forces convey energy into other forms. So they take energy out of the system. So an example of that would be friction. And we lose energy to heat and sound. So if there's no dissipative forces, doing work on a particle, then any gain in potential energy will give you a loss in kinetic energy and vice versa. So I'll go over an example to show you what I mean by that. You might want to pause and copy some of that down. So we're going to have a slope, and we're going to have a particle moving down the slope, and it's going to be a smooth slope, so that the only force acting is gravity, and we're going to ignore air resistance as well, and the particle is going to move from A to B. That's my particle. And it's going to start at 0 meters per second, and when it gets to B it's going to be travelling at 6 meters per second. The mass of the particle is 0.5 kilograms, and we want to find AB. So it's tempting to start trying to treat this like a SUVAT problem, and you shouldn't really need to use SUVAT equations in energy problems. This angle's 30 degrees here. Obviously they might bring in some SUVAT questions, but generally they're energy problems. So we can think about the gain in the kinetic energy and kinetic energy is a half v squared, where v is the speed, not the velocity, the speed of the particle. So we finish on a half times m times 6 squared, and we started with no kinetic energy because it started from rest, and so the gain in kinetic energy is 9 joules. So therefore the decrease in potential energy, because there's no other forces acting, is equal to 9 joules. The decrease in the potential energy is going to be mgh, where h is the height the particles drop down by moving along the slope. So 9 is equal to m, which is 0.5, times g, 9.8, times h, which makes that height equal to 1.8367 metres. That's a bit too accurate, but because I'm using the answer again, I'm going to leave it like that for now. And then to find this length AB, we can just use trig. So this angle here is 30 degrees. And we know that sine of 30 is equal to h over AB. And so AB is equal to 1.8367 over sine of 30, and that gives you 3.7 metres to 2 sig fig. So to start with, I just want you to look at some conservation of mechanical energy questions. So it's basic kinetic energy going to potential energy, or vice versa. So online textbooks, I don't have your class textbook at home, so it will have to go online. So exercise 2C, question 1, question 2, question 6, and then 11, 12, 13. So I think they start in a line and then they move on to slopes here.